Okay, so let's have a look midpoint first up. We've got the rule up there, so it's just adding the x coordinates divided by 2 at the y coordinates divided by 2. So in here we can see negative 1 plus 3 over 2 and 2 plus negative 2 over 2, and to simplify that gives us 1 and 0. The length, so the length is just really derived from our Pythagoras' theorem, if you remember. So it's just, AB all squared equals hypotenuse adjacent squared, hypotenuse squared, etc. So 3 minus 1 all squared plus 2 minus negative 2 all squared, so they both become positives. 3 minus 1 is 4 squared, plus 2 minus 2 is also 4 squared, so we end up with the square root of 32. We should look to simplify that, the square root of 16 by the square root of 2, which is 4 root 2. Our gradient rule, we should really be remembering this from last year. The gradient of any line, rise over run, which is y2 minus y1 over x2 minus x1. Doesn't hurt at this stage of the year to write the formulas down, write the rules down just so you remember it every time. Negative 2 minus 2 over 3 minus 1. Just make sure you don't confuse or mix up the x2, y2, x1, y1 points. And we get a gradient of negative 1 there. So to find the equation of the line, typically most of us like to use y equals mx plus c, so we need the gradient and a point the line goes through. So the gradient was negative 1. And we could pick any point up there. So I've just picked the point negative 1, 2. So we substitute the point in there for y and x and solve for c. So minus 1 is a plus 1. So we subtract that from both sides and we'll end up with c equal to 1. So then write out the equation of the line. So y equals minus x plus 1. Now for perpendicular lines, remember, so this little symbol for perpendicular, the product of the gradients is equal to negative 1, which means m2 is equal to negative 1 over m1. So the gradient of our line was negative 1, so negative 1 over negative 1 is positive 1. So the gradient of my perpendicular line is positive 1. So again, y equals mx plus c, so in this case m is 1. So y is equal to x plus c. But again, we substitute a point in. I guess we'll assume that the gradient of the line had to go through the point negative 1, 2. So we probably should have been told that. So substitute that point in and we'll get c there is equal to 3. So a gradient of the line perpendicular to AB is equal to x plus 3. Now as it turns out, if I read the question properly, it was only after the gradient, wasn't it? So we could have stopped where the gradient was equal to 1. So we didn't need the equation of a line there. Read the question, Mr. Gale. But the perpendicular bisector, this time we need a specific point, and the bisector goes through the midpoint. So from earlier we saw the midpoint was negative 1, 0. So here's where we find out the equation of our line. So we substitute negative 1, 0 in. We know the gradient of our perpendicular line is positive 1. So again, rearrange, we'll get c equal to 1. And so my perpendicular bisector is x plus 1. Now we'll just come up here to the right hand side. So if points are collinear, it means they lie in a straight line. So if the points A, B and C are collinear, and we'll probably see that up here, it means that each section, the section from A to B and the section from B to C, must all have the same gradient. So if we illustrate that, you can see the points there, A, B and C. And so A to B must have the same gradient from B to C. So I'm sure we've done some work here. We've got the gradient of A to B, and that gradient is negative 1. And so that needs to be the same as the gradient from B to C. So the point C is K5, and the point A is negative 1, 2. So instead I've gone from A to C, which you can see there, it's the same gradient. So y2, 2 minus 5 over negative 1 minus k. That has to equal the gradient of the line from A to B, which is negative 1. So if we simplify our left-hand side, we get 2 minus 5, which is negative 3 over, we'll take the negative sign out, negative 1 plus k, so those negatives cancel, that's equal to negative 1. So it's probably simplest if we multiply 1 plus k across onto the right-hand side. We'll have 3 equals negative 1 times 1 plus k. bring negative 1 back to the left-hand side, subtract 1, and k equal to negative 4 will give me a solution. Okay, so if we do a quick sketch of our graph here, 5 minus x, so a y-intercept of 5 and a gradient of negative 1, so both intercepts will be at 5. But we've got to restrict that domain, so let's restrict it down from x equal to negative 2, so it just shortens it there at the left-hand side, and at x equal to 7, so we've got a couple of endpoints there that we can label, haven't we? So at the left-hand side, at x equal to negative 2, y would equal positive 7, so we've got the point negative 2, positive 7 there. And at the right-hand side, if x is equal to 7, I get the point 7, negative 2. So now that we've got the graph, the range is really quite straightforward, isn't it? So the lowest value there is at negative 2, and the highest value there is at positive 7, and both are square brackets, so the range is from negative 2 to 7. Again, a midpoint. We've done a midpoint before, but this time now we've got a variable in our second point. So the midpoint still though is just x1 plus x2 over 2, y1 plus y2 over 2. So 0 plus d over 2, negative 5 plus 0 over 2. And to simplify those where we can, 0 plus d is just d, so we get d on 2 or a half d. And the y coordinate will be negative 5 on 2. So just apply the same processes there. Geez, that looks like a 3, doesn't it? Should be a 5 if it is. Gradient of a line perpendicular to the line. So first things first, we need to find the gradient of this line that we're talking about. So y2, negative 4 minus 0 over 0 minus minus 2. So negative 4 over positive 2, which is negative 2. A line perpendicular to that is negative 1 over negative 2, which makes it positive a half. So that's the gradient. Okay, so simultaneous equations, solutions that give our points of intersection. So if our lines are parallel, we won't get a point of intersection, so we have no solution. If the graphs are the same, there are infinite solutions. In other words, they repeat and they intersect infinitely. Both of those situations give us a determinant of the matrix that we use to solve equal to 0. So let's have a look at this example here where I left the little x off, so it should be 3x minus 6y equal 5 and 2x minus 4y is equal to 10. One method is, let's just rearrange the equations. If they have no solutions, the lines must be parallel. So if I work out the gradient of one of those lines, we can see there that y is equal to negative 5 on 6 plus 3 on 6x. So the gradient of the first line is positive a half. So do the same thing here. Let's divide by negative 4 there, and we transpose our equations. And we see M2 is also positive a half. So the two gradients are the same, hence the lines are parallel. So we don't get any solutions. Another way that we could approach this is actually to use a matrix approach, and either method is fine. So what we aim to do is set up a matrix that would solve these simultaneous equations. So we look at the first equation, we have 3 and negative 6 multiplied by xy down there, and that would be equal to 5 in the top right corner. Put my second equation in, and we'd have 2, negative 4 for 2x minus 4y equal to 10. So for no solutions or infinite solutions, the determinant has to be 0. So the determinant is the top left, so 3 times negative 4 minus negative 6 times 2. So negative 12 minus minus 12 would give me 0. And since the determinant is equal to 0, we have either no solutions or infinite solutions. Now from the equations, because the two intercepts are different, we can tell that there are no solutions. Looking down at example 3, do exactly the same thing. We might set up a matrix equation because I think it's a bit easier. So M3, 2, m plus 1 in the matrix, and that are the values that we'd use for our determinant. So m times m plus 1 minus 3 times 2, that's my determinant formula, would give me m squared plus m minus 6. And if that's equal to 0, we know we have a problem. So if I factorise that, I get m plus 3, m minus 2. which means m could equal -3 or m could equal +2, and that would give me either 0 or no solution, or infinite solutions, I should say. So we need to check. All right, so for unique solutions, it means m can't be -3 or 2. If it's not -3 or 2, it means we don't get a parallel line or the same line. So m is equal to any element of R except for -3 or 2, and k could be any value because it doesn't matter. If the lines aren't parallel, well then k can be anything. What about for no solutions and one solutions? So we need to check the values first. So let's put m equal to -3 or 2 and try and find out an appropriate k value so that the y-intercept is different. Okay, because if the y-intercept is different, we have parallel lines. So if we put m equal to -3 first, substitute it to the equations, I get -3x plus 3y is equal to 5. And if we transpose that straight away, that'll give me y is equal to 5 plus 3x all over 3. So let's write 5 on 3 plus 3x on 3, which is just x. So you can see there, there's equation 1. If I put into equation 2, m equal to -3, I get 2x minus 2y is equal to k. Transpose, take the 2x across, divide by -2. I'll get -k on 2 plus x. So if I want these two lines to be different, the y-intercepts have to be different. So that means I can't have -k on 2 equal to 5 on 3. So if I rearrange, multiply by -2, I'll get k can't be -10 on 3. So where does that leave us? So if m is equal to -3 and k is equal to -5 on 3, that would give me the same gradient and the same y-intercept. So that means they'd be the same line, and therefore I would get infinite solutions. So then if m is equal to -3 and k doesn't equal 5 on 3, or should be -5 on 3, shouldn't it? The lines would be just parallel, and so we would have no solutions. So there are the possibilities for m is equal to -3, but that k value should be negative, shouldn't it? Let's come over here to the left-hand side and check where m is equal to 2. If I put m equal to 2 in there, I get 2x plus 3y is equal to 5. And I get 2x plus 3y is equal to k. So clearly, if k is equal to 5, I have identical lines. So that's simply going to mean then if m is equal to 2 and k is equal to 5, we have the same line. So that would give me infinite solutions. And obviously then if m is equal to 2 and k doesn't equal to 5, well, all we would have is the same gradient but different y-intercept, so just parallel lines. So that would give me no solutions. Okay, so let's have a look at one of these trial paper questions. Initially it says find the solution when k is equal to 1, interpret. So if we just put k equal to 1 into the equations, I get 2x minus 1 is equal to y, x plus 1y, so x plus y is equal to 1. So k is equal to 1 in both cases. Use the elimination method, add the equations, 3x equal to 2, and we get x is equal to 2/3. And if x is equal to 2/3, well, I can substitute that back into, what have I done, equation 2 there. Y is equal to 1 minus 2/3, which would be 1/3. So we get the point 2/3, 1/3. So graphically, we'd argue that that's simply the point of intersection. Part B, well, what if we just work with a general solution? So maybe it's easiest if I label the two equations 1 and 2. And we'll see that if I rearrange equation 1, I get y is equal to 2x minus 1. And what I might do now is substitute that y equal to 2x minus 1 into equation 2. So x plus k times y, that's where the 2x minus 1 comes from, is equal to k. Expand that bracket, x plus 2kx minus k equals k. And now I'm going to group my x terms together. So if I take x out as a common factor, I get 1 plus 2k. and then take that negative k across to the right hand side, and I'll get x equals 2k plus 1 on 2k. So there's my x value. So what I normally do when I get my x value, I substitute that in to get my y value. So probably into equation 1 is the simplest of those, because I already know y is equal to simply 2 times x minus 1. So x is 2k plus 1 on 2k. So 2 times that minus 1 is equal to y. Oh, well, minus y is equal to 1. Transpose. So 2 times that, 4k minus 1 is equal to y. So let's get a common denominator there. So let's write it as y is equal to 4k over 1 plus 2k minus 1 plus 2k over 1 plus 2k. So that's the same as 1. And now we can just add those numerator values together. So 4k plus or minus 2k is 2k. And we have a minus 1 there. So y is equal to 2k minus 1, 1 plus 2k. So there's my solution in terms of k. Okay, so if I put my x coordinate in, go back there, 2k plus 1 on 2k, and my y coordinate is 2k minus 1 over 1 plus 2k. Part C. We've just done a quick check there. If I put k equal to 1 in there, you see I can get 2 on 3 plus 1 on 3, which is what I should have got, which is what I got my first got the first time. So that's a nice little check to make sure my general solution at least matches off my initial solution. For no solution, how do I get no solution? We'll have a look at the k coordinates there. I won't get a solution here if my denominator is 0, will I? So the denominator in both of those x and y coordinates is 1 plus 2k. So if 1 plus 2k is equal to 0 or k is equal to minus a half, I won't get a solution. What does that mean graphically? Well, it means that graphically, if I put that k equal to minus a half into equation 2, you'll get x minus a half y is equal to minus a half. If I rearrange and simplify, perhaps take the half across and get a half y to be positive, then multiply through by 2, I can see y is equal to 2x plus 1. And the other equation is y is equal to 2x minus 1, so they're parallel lines. That's why there's no solution. Okay, so to solve a 3 by 3 set of equations, it really is CAS driven. So we're going to use a CAS calculator to solve the equations, but we still need to be able to set up the equations. So we're going to need 3 points. Now, the graph itself passes through the origin, 0, 0, and those are the 2 points. So if I substitute point 1 in, which is the point 0, 0, into the equation y equals 2x to the 4 minus x cubed, I'm just going to end up with an equation where d is actually equal to 0. So there's one of my unknowns, if you like, that I had to solve. If I now substitute the point -1, 5 into the calculator, in other words, x is -1, y is 5. So you can see there 5 is equal to 2 times -1 to the power of 4 minus -1 to the 3 plus b times -1 squared, etc. Notice the -1 in a bracket to the power, just to try and keep the negative sign straight. If I simplify that expression, I'll get 5 is equal to positive 2 plus 1 plus b minus c. And you could argue it could easily be a plus d at the end if I wanted to have a 3 by 3 equation. Rearrange that, and I get b minus c. And well, I'll put the plus d in there simply because the question said to have the equations involving b, c, and d. So transpose that, and we get b minus c plus d is equal to 2. There's equation 2. Do the same thing with point 3, which is the point 2, 3. Y is equal to 3, x is equal to 2. Substitute the 2 in for x all the way along. Be careful of signs. The powers 2 to the 4 is 16. It's not 8. So I'm going to get 3 is equal to 2 times 16, which is 32, minus 2 cubed, which is 8, plus 2 squared, which is 4b, plus 2c plus d. So if I rearrange that, 32 minus 8 is 24. Take 24 across to the other side, and we get -21. No. There we go. So there's my three equations. Okay, so they're the three equations that I needed. So I need to set this up as a matrix to solve those. So as a matrix, I put in all the coefficients, the unknown values. So for the equation 1, there was 0b plus 0c plus 1d, hence the b, c, d there. And they were equal to, well, the first point's equal to 0. Equation 2, it was 1b minus 1c plus 1d, and that was equal to positive 2. And we had 4b plus 2c plus 1d, and that was equal to negative 21. So if we use our technology there with our calculator, just solve that system of equations, we'll get a set of solutions.